What up, guys? Today we are going to do something a little different, and as I said in the last video, I want to try working out more and more exercises. So today we're going to talk about linear dependence. I'll be covering a few exercises, with the first couple being from Shankar's Principles of Quantum Mechanics. You can find that on page 5. It is exercise 1.1.5. The first one is show that the row vectors 1, 1, 0, 1, 0, 1, and 3, 2, 1 are or are not linearly dependent. We'll begin by breaking down the problem by each step, so that way after you guys watch this video you can better understand how to solve these problems on your own, because what good is just knowing the answer. Our first step is to analyze the problem. So we see that it said row vectors and not column vectors. That means we can construct our given vectors, and I'll be using Dirac notation because in quantum mechanics Dirac notation is big, so the earlier we start implementing Dirac notation the better off we'll be. Let's define our first vector to be v1, and I put it as a ket. I believe it would be a bra if it's a column vector, but I don't think that matters too much as of right now, because the point is to show linear dependence, and that's the concept. And we can set it up like this, and we can set up our second vector similarly. You don't need to put the commas when you make matrices, but it is helpful to do so just in case this is your first time using matrices. And we set up our third vector as follows. So now that we have the basis of our problem set up, we need to figure out what it means for something to be linearly dependent. We can see that the corresponding matrix and system of linear equations can be represented as 1, 1, 0, 1, 0, 1, and that its linear system would be represented as x1 plus x2 equals 0, x1 plus 0 equals 1, and that 3x1 plus 2x2 equals 1. You can also refer to the ones as x3, but for simplicity, we'll just refer to them as 1 since this problem is pretty simple. Now we move to step 4, our final step, which is test your definition and your hypothesis. Now that we have the matrix and its corresponding linear system, we can test to see if it's linearly dependent, if there's some way to construct v1, v2, or v3 by plugging in values for x1, x2, and x3 such that it satisfies all conditions of our linear system. And you can think of the first line, second line, and third line of our linear system as the 3 conditions that it must satisfy in order to be linearly dependent. That's given that x1, x2, and x3 cannot be 0 and are not equal to 0. Now that we have everything in place and we've set up the question correctly, we can see that if x1 plus 0 is equal to 1, then in order for the first system or first condition to be satisfied, x2 must be the inverse or the negative value of x1, which means that, if x is 1, x1 is equal to 1, then adding x1 plus x2 should equal 0 if x2 is equal to negative 1. Similarly, if x1 is equal to 2, then x2 must equal negative 2. Now we construct our values for x1 and x2. For simplicity, we'll set x1 equal to 1, and that means that x2 must equal negative 1 since x2 is the inverse of x1 or the negative value of x1. And that satisfies our first two conditions since 1 plus negative 1 is equal to 0 and 1 plus 0 is equal to 1. We can see that the third condition is then satisfied since 3 times 1 is 3, adding that to negative 2, which is a result of 2 times negative 1 is equal to 1. For our next exercise, we'll be doing the other part to Shankar's exercise in 1.1.5, which states that given the row vectors 1, 1, 0, 1, 0, 1, and 0, 1, 1, prove or disprove that this vector space it describes is linearly dependent. We've analyzed the problem, we've set up the question in a reasonable way, and step 3 is to figure out what the problem you're trying to solve is on a deep scale and identify the definition and tools needed to solve it. We can show that the vector space V is linearly dependent if we can construct the vectors v1, v2, and v3 using 2 of the 3 vectors. So the first step is to analyze the question. So what is it telling us? It's telling us that we have row vectors, which is stated, and that we must construct the vectors of this vector space in such a way that corresponds to our problem. Before we head to our second step of constructing the problem, now would be a good time to pause and see what you get. Our second step is to construct the problem, and we see that the row vectors can be constructed as follows. We let vector 1 be the matrix corresponding to 1, 1, 0. We let vector 2 be the matrix corresponding to 1, 0, 1. We let vector 3 be the matrix corresponding to 0, 1, 1. Before we head to step 3, what would be the corresponding matrix and what would be the linear system describing that matrix? Now would be a good time to pause before we head to the next part. We can see that the corresponding matrix would be as follows, where the row vectors are 1, 1, 0, 1, 0, 1, 0, 1, 1, and its column vectors would be 1, 1, 0, 1, 0, 1, 0, 1, 1. And it represents the linear system x1 plus x2, which is equal to 0, x1 plus 0, which is equal to 1, and 0 plus x2, which is equal to 1, where we let x3 equal 1 respectively for simplicity. Can you describe what the definition we would use is and how that would lead into our hypothesis to test this? Step 3 is figuring out what tools and definitions are required to solve this problem. More specifically, figure out what tools and definitions are required to form our hypothesis or test our hypothesis. We can test a system of vectors' linearity or its linear dependence if there's some way to construct vector 3 using vector 1 and vector 2, where our matrix is represented by the vector space V, representing the system x1 plus x2 equal to 0, x1 plus 0 is equal to 1, and 0 plus x2 is equal to 1. If you'd like to pause and solve it yourself before seeing the solution, now would be a good time. So in step 4, where we're testing it using the information we gathered in the prior steps, we can test the following conditions of our system, where we let x3 equal 1. So in condition 1, we see that x1 plus x2 is equal to 0. So if x1 plus x2 is equal to 0, then what is x1 and x2? In order to understand that, we need to find those values, and x2 must be the inverse of x1, represented by negative x1, or vice versa, since we don't know the value of x1 yet, where x1 is equal to the inverse of x2. However, since x1 is equal to 1, and condition 3 tells us that x2 is equal to 1, since adding 0 to anything results in that value, an unchanged value, then there's no way to satisfy condition 1 for any corresponding value of x1, x2, or x3 not equal to 0. Therefore, this vector system is not linearly dependent, and in fact is linearly independent, which is why both those problems were in the same exercise. Now we head to our final exercise 2.1 on page 63 of the Quantum Computation, Quantum Information book by Nielsen and Chuang. The question states, show that the vector 1, negative 1, the vector 1, 2, and the vector 2, 1 are linearly dependent. And in our first step of analyzing the problem, we can clearly see that the only answer for this is for it to be linearly dependent. Another step that I added that I didn't do prior that you can do is to draw a figure or draw a graph representing these coordinates, working out that these coordinates represent a triangle, where vector 1 plus vector 2 is equal to vector 1 plus vector 2, which would result in our vector 3. Now in constructing our answer, we let v1 or vector 1 be the column matrix 1, negative 1. We let vector 2 be the column matrix 1, 2, and vector 3 be the column matrix 2, 1. Then the corresponding matrix would then become 1, negative 1, 1, 2, and 2, 1. And if you look at it as a row matrix, you can see that it's 1, 1, 2, negative 1, 2, 1, which would be very similar to our last problem. The corresponding linear system would then be x1 plus x2 is equal to 2, and negative x1 plus 2x2 is equal to 1. Before we head into the proof of our answer, can you determine what the answer would be prior to doing the work for it? Using the information we gathered in the prior steps, we can see right away that the system is linearly dependent, since adding v1 and vector 2 results in vector 3 for any x1, x2, and x3 not equal to 0. And using the figure above, we also see that it satisfies the laws of a triangle. The square of vector 1 added to the square of vector 2 results in the square of vector 3. In addition, setting x1 equal to 1, x2 equal to 1, and x3 equal to 1 will result in 0 for our given matrix, or even setting x3 equal to negative 1 would result similarly and satisfy all conditions. That concludes today's video, guys. I hope you enjoyed. I will attach a PDF of a more detailed description. Have a good day. Stay learning.